Hello, everyone. Welcome to Product at Scale conversation about building crowdsourced maps for autonomous driving. In today's presentation, we will cover a few different areas. We will start with discussing the need for HD maps. We will then discuss the advantages of crowdsourced HD maps. We will spend some time discussing the challenges of building such maps and how NVIDIA intends to solve them. We will wrap it up with doing a deeper dive into the process of creating an HD radar map from multiple crowdsourced map streams. So let's start with, why do we need HD maps at all? After all, we can drive without a map. Why can't a car drive itself without a map? Well, there are quite a few reasons that we use the HD maps for in our AV solution. The first reason for us is to validate our operational design domain. Is the car driving on a highway? Should a feature like automated lane changes be enabled on a highway? Maps help us decide if the vehicle is driving within the operational boundaries for a particular feature. We then use a map to do both course level route planning and more detailed level lane planning. This helps the system know what maneuvers need to be done to enable an AV to reach its destination. Maps also help us drive safely and provide a comfortable ride to the occupants of the vehicle. They provide a nominal path and information like speed limits and signs to be obeyed on the road. It also improves comfort of the drive by providing information like curvature of the road so that an AV can reduce its speed and adjust driving maneuvers as a curved road is traveled through. Maps are essential when we start driving in more complex environments, which contain things like traffic lights, roundabouts, and other harder features for an AV to navigate. Maps provide details that an AV can use to drive through such a complex environment. So the traditional approach for building HD maps, which we still do today, is to have survey cars. We use these survey cars with very accurate sensors. We drive them around to collect data. You might be used to seeing these cars driving around on the road from various different companies. This data is then curated using automation, but a lot of manual labeling to create detailed, highly accurate maps for driving. Though these maps are of excellent quality, they do have some downsides. The main problem with this approach is that it is very expensive to create these maps and very expensive to keep it up to date. The data collection and the labeling process that is used is very time consuming and expensive. Covering the entire road system of the world and keeping it up to date is a hard problem to solve with this approach. So we started looking at alternate approaches to solve this problem. So we went to crowdsourced maps. Crowdsourced mapping starts becoming an option as we start seeing more consumer cars with sophisticated perception capabilities on them. The advantages of such an approach are that the sensor suite that is on the consumer cars is overall inexpensive. After all, you've already bought the car with the sensor suite. There is no need for a dedicated data collection process. After all, you're driving your commuter route. As AV-equipped cars are driving around the world, they're always collecting data. This data is then used by us to create a map. This model allows for very fast updates of the map and allows for real-time changes in the world to be reflected in the map. This approach also provides us with richer data across a larger area than survey cars can ever achieve. A survey car driving through every neighborhood or through your driveway is just a very hard problem. One additional advantage of this approach is that maps can now be more intelligent. They can learn from driver behavior. They can learn how the commuter drove. They can learn how commuters around the ego car are driving. Some examples would be typical speeds that a road is driven at, or how a particular lane might be traversed. So how do we go about building crowdsourced map? At NVIDIA, we are building an autonomous system that has world-class perception capabilities. This is the basic component that we leverage in map making. We like to think of our maps as perception history. We record the world as consumers drive and create a collective history. And to do this, we leverage NVIDIA's compute capabilities in the car on Drive Orin and DGX infrastructure in the cloud. As part of our Drive AV product, we are focused on building DNNs to perceive all kinds of static and dynamic data we see in the world. These DNNs enable us to drive in the world and in addition are the backbone of the mapping subsystem. For mapping use, we divide this data into 4 different classes. First, we are interested in any data that we can add to the map so that a vehicle can localize itself in the world. This data can be features like road markings, lane dividers on the road. It can be poles or any vertical landmarks. The second group of data is road content that helps us create a lane graph for the vehicle to follow. This includes paths, dividers, road boundaries. The third thing that we are interested in understanding is the rules of the road and recognize static content on the road that impacts driving decisions. This is data like traffic lights, speed limit signs, wait lines at an intersection, other signs which might allow driving on a certain road or not, parking spots. And lastly, we are also interested in how vehicles around us are driving. As I previously said, this data can be used for a variety of purposes. One thing it can be used for is to infer the structure of the road that might not directly be visible to us. So how do we take this data and put it into our mapping subsystem? In this video, you will see one of our AV vehicles driving in Seattle downtown. As we are driving, we are perceiving the content in the world. On the top left window, you will see the live perception results. In the bottom, you see a construct that we call MapStream being generated for the same area. And then on the right-hand side top window, you're seeing the MapStream projected back into the camera. MapStream is a consolidated and efficient representation of the perception data that we talked about in the last slide. In addition to the perception data from cameras, we also include processed radar point cloud data and information from the IMU and GNSS system. This data is compressed to ensure that we can upload it with the lowest bandwidth usage. Privacy and region-specific requirements play a very important role in how this data is processed also and what it can contain. So once map streams are ready, we have map streams being uploaded from vehicles across many OEMs, and they're all arriving to the mapping cloud. They then undergo a 3-step process to convert them into a map. The first step is registration. Because map streams arrive to us from many different vehicles, each generating their map stream from a unique driving position and angle, the data first has to be normalized. The second step for us is an AI-heavy process where the normalized data is fused together. In this step, we resolve for all of the minor variations of perception results that can be caused by vehicle-to-vehicle differences, such as tire pressure, suspension. Lastly, for maps that are used in higher levels of autonomy that require safety certification, we manually verify and make any necessary edits to them before publishing. Because we leverage AI to scale this effort, all of these 3 steps occur on NVIDIA's own enterprise AI hardware called DGX pods, as well as our own ML ops platform called maglev. Because for mapping, privacy and data export laws vary country by country, this infrastructure was built in a way so that different instances can be deployed and customized for each region that we operate in. This distributed deployment model also eliminates single points of failure and keeps our cloud more resilient. So what do we get out of it? The output of the steps before is our map. Again, you see the same area of Seattle downtown, but now we are processing data from multiple drives and creating maps from it. These maps have been created with an average of about 2 to 4 commuter drives per lane, which were collected in different weather conditions. Seattle, where our team is based, is blessed with rainy season through a large portion of the year. So we quickly had to make sure that our product was resilient to weather changes on the road. In the map, you see green lines for paths, and you see cyan lines showing the center of the paths and wait lines. In addition, you see vertical landmarks called poles that could represent different kinds of vertical elements seen in the environment. You also see traffic lights and signs. And lastly, you see how we associate each of the traffic light and sign to a particular lane so that you know what rules apply as you are driving in the lane. So, of course, any such new endeavor comes with its own set of challenges, right? I'm going to go over a few set of challenges that we have encountered while building crowdsourced mapping product and how do we try to solve them. First, we are doing extra work here on the AV itself, right? Where compute cycles are always hard to come by. So we have to leverage and reuse as much of the perception results as possible. So that's our 2-pronged approach. The first, to reuse perception results. And the second is to run CUDA optimized lightweight algorithms that leverage the perception results we've got extremely efficiently. The second challenge for us is bandwidth. We would like to be as efficient as possible with the size and the frequency of the data that we upload. The first optimization we apply is to not send all perception results to the cloud. We instead process multiple frames and consolidate observations. For example, if a sign is seen multiple times by the camera over a short period of time, we do geometric optimization to infer location of the sign from each observation. We then send a single sign observation to the cloud. We also apply compression techniques that are unique to each kind of data to leverage its properties most efficiently. Our third challenge is to build an automated map engine where map freshness is guaranteed with a very high SLA. To do this in the most efficient manner, we implement map health monitors that are running on the cars constantly. These help us reduce the data that is being sent to the car, because if the map is good, you don't need to send any more data, right? And it also reduces the compute on the service so that cars are not sending data all the time to the server. They're only sending data up when a new map is needed for an area or a map update is needed for an area. To ensure that we can update these maps very efficiently, we split the world into smaller units of execution. We then locally optimize each unit of the update of the map. We support elastic compute of the map update to ensure spiky patterns caused by road changes in a particular area or additional vehicles in an area can be handled. Our algorithms are all optimized to run on DGX pods, as we mentioned before, and we leverage various NVIDIA GPU acceleration techniques wherever applicable. And the system is built to rapidly notify the cloud and then the car about the staleness of the map. We, of course, also need to handle legal restrictions. We need to build a solution that can be deployed both locally, and the solutions need to be able to run on public and private clouds based on the laws of a particular country. We need to be able to restrict map creation in certain areas, and we need to apply anonymization and GPS scrambling techniques wherever applicable. So a lot of different challenges, but out of that comes the map that we just showed you. Just to give you an idea of the scale of compute that we are working with, here is a brief overview of it. We are building a system that will handle data from tens of millions of cars, has to update various geographic regions with thousands of updates at any given time. And all of this is done using our GPU accelerated algorithms. I will now talk through a case study of building radar maps to show the approaches that I just talked about and how they are used by our system in building maps. So we'll start with map streams. The radar map stream module in the car receives radar point sweeps. In the left picture, we illustrate the relationship between radar detections collected over a short span of time. These short sweeps can be packaged into one or multiple map stream packets. We also apply filters for dynamic objects and ODD-specific filters for reflectivity levels. So if you're in Utah in a desert, we will collect more data. But in San Francisco downtown, we will use reflectivity values to suppress the amount of data we are collecting. We also suppress data collection when the car is idle, right? So all these techniques are used to help with reducing the data size of the radar packets. But simply uploading the radar accumulator packets that we just generated still results in large network bandwidth consumption. So let's see how we compress the radar point clouds as the next step into map stream packets. So the raw point clouds take a lot of network bandwidth. So we compress and convert them into map stream packets. We create a fine resolution grid around the pose of the radar map stream packet and quantize the radar point cloud onto this grid. The quantized data is then tiled into larger cells, and compression is applied to each spatial cell by spatial differencing of consecutive values. And then as a final step, we apply Huffman encoding. So all these steps are done to compress the data into the smallest radar map stream packets that we can create. As you remember, we talked about bandwidth being one of our big concerns, right? So now these in-car created radar map stream packets can be transmitted up to the cloud. Once map streams have been uploaded to the cloud, Now we follow the same workflow that we would do for other mapping data. The first step for the mapping pipeline is always to find relevant map streams. The map stream selector is trying to find geometrically overlapping map streams, and then it feeds those map streams into the registration module. The main purpose of the registration module is to find a geometric relationship between pairs of drives in locations where they overlap and create relative pose links. These relative pose links allow us to place two map streams into a common coordinate system. And this is really needed to align landmarks and all the other features that we talked about in the map across different layers of the map. The next step is pose optimization, which allows us to do global registration of all drives and all map layers. Lastly, the fusion step generates a more complete point cloud for radar, and this is much better than the individual point clouds that you would have seen from an individual map stream. All of this work that I described here is done using CUDA-optimized algorithms on radar layers represented as images, allowing us to do simple, efficient operations. The output of these steps is radar maps, which are then delivered to our cars. Here we show a small set of radar maps in different diverse scenarios. The first one that you see is an highway exit scenario. Then you see a suburban driving scenario. And the last one is a downtown urban driving scenarios. And you see high quality of maps and us localizing really well on the maps. So that brings me to the end of our talk. As you saw, crowd maps are not easy to build, but it allows us to enable automating your entire drive, right from your garage at home to your office parking lot, or right from your garage at home to your vacation home in summer, all completely automated. Thanks a lot for taking the time to watch this session. We will finally close with showing you an automated drive in Santa Clara, starting from our gorgeous office building.